Hello everyone, myself Vinay Kumaram. I am pursuing PhD in physics. So in this particular YouTube channel, I will be teaching physics, chemistry and mathematics starting from 8th standard till 12th standard. So if you want to learn physics, chemistry and mathematics, then please do subscribe to my channel. So in my previous video, I was actually discussing about the 11th chapter of 9th standard science subject that was on sound. So in that video, I have given a brief introduction about sound and how sound requires medium to propagate from one particular position to other position. So in this particular video, we will learn some of the characteristics which are associated with this particular sound. So in my previous video, I have explained you that if you strike a tuning fork, so this tuning fork will be vibrating along its mean position, and because of these vibrations, there is high pressure regions and low pressure regions created among the air molecules around this particular tuning fork like this. So this high pressure region can be known as compressions and low pressure region. So that means here air molecules which are there immediately after compressions have low pressure, and this low pressure region can be known as rarefactions. So this you can refer my previous video and I have explained about this. So always remember, in compressions there is high pressure and in rarefactions there is low pressure, and because there is high pressure of air molecules at this particular space, hence density at this particular position, that is density at compression region. So this is compression region. So density at compression region is high and density at rarefactions region is low, because here air molecules has been compressed at that particular compressions region, hence there is high pressure of air molecules, and because they have been compressed in a smaller volume, hence density is higher at that region, and in rarefactions air molecules have less pressure, hence their density will be less. So here, to understand how this particular propagation happens, we can have a graph like this. So for example, if you have density along this particular y-axis and if you have direction of propagation like this, so now we have direction of propagation like this. So this is direction of propagation of a particular wave, let's say longitudinal wave. So here you can see there is compression region and a rarefaction region. This compression and rarefaction is transferred to the next set of molecules and it creates another pair of compressions and rarefactions. So again there is one set of compressions and one set of rarefactions like this. So like this it goes on. So again this will transfer to another compressions and rarefactions. So there is set of compressions and rarefactions, compressions and rarefactions, compressions and rarefactions, which goes on like this through the medium. So that means here there is a region of high pressure or higher density and lower density, and there is a higher density and lower density, and there is a higher density and lower density. So that means the vibrations which are creating this high density and low density region, you can write it in the form of waves. So here you have high density at this particular position, and moving forward there is low density at this particular region, and moving forward again there is an high density, and moving forward again there is a low density, and again there is an high density, and again there is a low density like this. So that means here the disturbances or the vibrations which has been created by the tuning fork is propagating through the medium, and here particles are not moving from one position to other position. The vibrations which are generated because of the vibration which has been generated by that source, for example here tuning fork is the source, so vibrations which has been generated by the tuning fork is transferred to the air molecules, and every air molecule transfers that particular vibrations to the next air molecules. So this process continues, and hence there is high pressure, low pressure, high pressure, low pressure, or high density, low density, high density, low density regions created in the air molecules. So because of this, there is a formation of wave a formation of longitudinal wave because this wave is parallel to the direction of propagation. So that's why here I have taken the high density region and here I have taken the low density region. So if you consider density along this particular axis, then this will be the high density and this region is low density. This region is high density and this particular region is low density. This region is high density and this particular region is low density. So how the compressions and rarefactions occur in the air molecules. Similarly, there is formation of high density, low density, high density, low density, high density, low density in the atmosphere. So that's why sound can be easily propagated from one position to other position. So this is a diagram of a particular wave. So now you have understood how this particular wave diagram I have created. So here in this wave diagram, this particular regions, so here what I have marked now, these regions are high density regions. So that's why these are compressions, because compressions create high density, and these particular regions are low density regions. So that is rarefaction regions. So that means here R will be there. So now again I will write this particular wave, another slide. So here in this particular wave, these particular regions are known as compressions. This particular region of a wave can be known as rarefactions, or this can be known as crest. So this is CREST, crest. This particular region can be known as trough. This region can be known as crest, and this region again it can be known as trough. And now I have told that we'll be discussing characteristics of sound in this particular video. So when you have to understand what do you mean by frequency, what do you mean by amplitude, what do you mean by time period, then you have to understand this particular wave diagram. So now we know that a particular wave comprises one crest, one trough, one crest, one trough, like this. So that is nothing but compressions and rarefactions. Compressions and rarefactions. So if you consider two consecutive compressions like this, or if you consider two consecutive rarefactions, then this can be known as wavelength of a particular wave. So this can be known as wavelength. And always remember, two consecutive compressions and two consecutive rarefactions will be having same length. So that's why you can either consider two consecutive compressions or you can consider two consecutive rarefactions. So here either you can consider two consecutive compressions or you can consider two consecutive rarefactions. Both will give you wavelength. Both of them will give you same wavelength, because the length between two consecutive compressions and the length between two consecutive rarefactions are always equal. Hence, either you can consider two consecutive compressions or two consecutive crests, or you can consider two consecutive rarefactions, or which is also known as troughs. So either you can consider the lowest parts, that is these particular troughs of this wave, or you can consider these highest parts, which is the crests of this particular wave. So if you are considering crest, then you have to measure the length between two crests. If you are considering trough, you have to measure the length between two troughs. So that will give you the measure of wavelength. So this wavelength is always denoted as lambda. So wavelength is always denoted as this particular symbol. So this symbol is known as lambda, which is a Greek letter. And this particular wavelength has SI unit, which is measured in meters. Because wavelength is again a length, so that's why even wavelength has SI unit meter. So now you have understood what you mean by wavelength. Now moving on to the next characteristic of sound, that is frequency. So what do you mean by frequency? Frequency of a particular sound is nothing but how often vibrations are occurring. So how often vibrations are occurring in 1 second or in 1 unit of time. So how often vibrations are occurring in a unit time. Unit time means in 1 second. So unit time means nothing but in 1 second. How often a vibrations are occurring can be known as frequency. So that's why frequency is known as 1 by T. So this is the symbol which we use for frequency. So if I have to just explain with another analogy, for example, if I have an object like this, so if I have an object like this, I am beating this object like this. So when I am beating this object, so how often I am beating this object in 1 second? So that means how frequently I am beating this object in 1 second of time. So how frequently I am beating this particular object in 1 second of time will be known as frequency of my beating. So if I start a particular stopwatch and in 1 second if I hit this particular object more number of times, so that means frequency is higher. And in same 1 second if I hit this object only like this 2 times or 3 times, so that means less number of times I am hitting this object, I am beating this object, so that means less frequently I am beating this object. And if I am beating this object continuously like this, that means I am beating more oftenly in 1 second of time. So that means how much amount of vibrations you are creating in one particular unit of time. So that is in 1 second can be known as the frequency of that particular sound. And that's why this particular formula comes into picture. That is frequency is equal to 1 over time. That is how frequently vibrations are created per unit time. So that's why time goes to the denominator. So frequency is equal to 1 over T and the unit for frequency is Hertz. So either you can write the full expansion of Hertz by taking H as small letter, or you can just make H as the capital letter and you can just keep it H as it is without expanding. If you are expanding, then H should be small. If you are not expanding, then H should be capital. So this is the SI unit of frequency. So always remember, frequency is always associated with the pitch of the sound. And always remember, amplitude is associated with the loudness of the sound. So what do you mean by loudness and amplitude? So remember, if I am hitting this object harder, that means I am generating more sound. And if I am hitting this object softer, that means I am creating less sound. So that means if I apply more energy, I am creating more louder sound. And if I am putting less mechanical energy, that means I am producing softer sound. So that's why here amplitude defines the loudness of the sound. So what do you mean by amplitude? For example, if I have a wave like this, so the height of this crest and the height of this trough can be the amplitude of this particular wave. So this particular distance what you are seeing here, so this can be known as amplitude of this particular sound. Or simply in general terms, if you want to understand what you mean by amplitude, amplitude is nothing but the loudness of the sound. It is nothing to do with frequency. Always remember, loudness and softness of sound depends on the amplitude. If amplitude is more, that means sound will be loud, and if amplitude is less, sound will be less. Frequency is different. Frequency is how often vibrations are created in a unit time. So that's why always frequency is associated with pitch and always amplitude is associated with loudness. Now coming to the speed of this particular sound waves. Now if you want to understand what we mean by speed of this particular sound, so always remember, speed depends on distance and time. So here distance divided by time you can take, and distance, in the place of distance I can take wavelength. So if a particular wave is propagating, means that particular wave will be having certain wavelength. So that wavelength you can consider as the distance traveled by that wave. and that distance is nothing but wavelength. So in the place of distance I can write lambda divided by t. So if you want to calculate speed of a particular sound, then you require wavelength, that is lambda divided by time. So lambda by t can be written as lambda into 1 by t, and we know that this 1 by t is frequency. So in the place of 1 by t I can write frequency nu. So always remember, this is known as nu and this is known as lambda. So this is v, which represents the speed of this particular sound. So v is equal to lambda into nu. So the product of wavelength and frequency will give you the speed of that particular sound. And always remember, sound, when it is traveling in different medium, it has different speed. Always remember, sound travels at higher speed in solids. So sound have higher speed in solids, and in different solids sound has different speed. So sound has higher speed in solids, it has medium speed in liquids, and it has least speed in, or sound has less speed in gaseous medium. So that means here in different gaseous medium it has different velocity, and in different liquids it has different velocity, and in different solids sound has different velocity. So always remember, velocity or the speed of a particular sound depends on the medium, whether it is solid, liquid or gaseous medium, and also it depends on the material of that particular medium. So for example, here in this textbook if you refer, whereas in nickel the same sound travels at 6040 meter per second. The same sound in steel, it travels at 5960 meter per second. So always remember, in different medium the speed of sound is different, and in different material also the speed of sound is different. And one more thing you should always remember, if temperature is increased of a particular medium, if temperature of a particular medium is increased, then sound speed will also be increased. So always remember, speed of this particular sound, speed of particular sound depends on temperature as well. So if temperature is more, then speed is more. So always remember, if temperature is higher, then speed of sound becomes higher. So that's why in normal air, if this normal air has 0 degrees Celsius as its temperature, then speed of sound is somewhere around 331 meter per second. So this is speed of sound in air which has 0 degrees Celsius temperature. If the same air has 22 degrees Celsius temperature, that means if temperature has increased to 22 degrees Celsius, then the speed will also increase. The speed of sound will also increase, and that is equal to 344 meter per second. So that means here speed of sound depends on the medium. So that is whether the medium is solid, liquid or gas, and also speed of sound depends on material. That is what kind of element is present in that particular medium. It depends on that as well, and also the speed of sound depends on temperature as well. So it depends on medium, it depends on the type of material, and also it depends on the temperature of that particular medium. And we all know light has 3 into 10 power 8 meter per second as its speed. So that's why whenever you see a lightning, first you will see the lightning and then you will hear the thunder. So why? Because when clouds generate the thunder, both lightning and sound happens together. That means both lightning and thunder happens together. But because light speed is more, first you see the lightning and then you hear the thunder sound. Because sound is just traveling at 344 meter per second speed at 22 degrees Celsius temperature in air. So this is all there in this particular video. There are few more concepts in this particular chapter. So those concepts I'll be teaching in my subsequent videos. Till then, if you want to learn more physics, chemistry and mathematics starting from 8th standard till 12th standard, then you have to subscribe to my channel. Please do subscribe to my channel and stay tuned with my channel. Thank you.